Today we have with us Chuck Russell. He's from the Desert Research Institute. He's also the UGTA Science Advisor, and his briefing is on ER 20-12, a case study of corrective action investigation in a challenging environment. So I'm going to go ahead and turn it over to Chuck. Thank you.
Thanks, Barb. The presentation I'm going to give you today is actually a paper that I presented at Waste Management, and a couple of you were there at that time. So its intended audience is a little bit different than you guys. There's some basic information here in this presentation about the site that you already know, so you'll have to bear with me. I didn't alter it in any way. And also I'd like to acknowledge my co-presenters on this paper, Nicole DeNovio, who's with Golder Associates, and Irene Farnham and Jeff Wirtz, who are with Navarro Research and Engineering. Okay, so the objective of this talk is to highlight actions taken by the U.S. Department of Energy's Environmental Management Program in Nevada as an exemplary approach. Thank you. As an exemplary approach to corrective action investigations under challenging conditions. So, as all of you know, the site has been used for nuclear testing from 1951 to 1992. The National Nuclear Security Administration is responsible for the overall management of the site, as well as for conducting ongoing security-related missions that are conducted at the site. DOE's Office of Environmental Management is responsible for remediating historic locations associated with past nuclear testing, both on the site itself and the surrounding NTTR, which is operated by the U.S. Air Force. The Underground Test Area Project is the EM program that is charged with characterizing the groundwater to address the impacts of the 828 underground nuclear tests that were conducted on the site. Those tests, which are shown here on this map, were grouped into 5 locations based on the proximity of the testing, similarity in geology, similarity in hydrologies. And these are the corrective action units that you've heard us refer to so many times in the past. The area that we're going to focus on is up on Paiute Mesa, and that's where the story that we're going to tell. So we're going to look a little bit closer at that, and specifically we're going to be talking about the unanticipated yet not unexpected detection of tritium in well PM3 and our evaluation of the potential sources of that tritium, as well as the characterization activities that followed. Paiute Mesa is an elevated mesa that comprises the northwest portion of the Nevada National Security Site. It covers about 630 square kilometers. Its elevation ranges from about 1,650 meters on the southern and northern edges to about 2,300 meters on the western edge. And in order to understand the story that I'm going to tell you, you have to understand a little bit about our prior conceptions of what was going on here. So, well PM3, which is where the tritium was detected, is right here, and one of our prime suspects is Handley, the underground nuclear test here. This whole area is underlain by a number of calderas, and these are the boundaries of the calderas, and they're connected with one another, or they're overlapping with one another. So the geology is quite complex. It's a very thick sequence of tertiary volcanics. And if you look at the hydrology, which the surface of the water table is shown here, you can see there's, under our prior conceptions, and we kind of believed this up to about 2007, we felt that there's this potentiometric trough, this trough in the water table that was causing water to flow from the northeast towards the southwest in this direction, and then from off the site towards on the site in this direction. And if you believe that, then well PM3 could be described as being up gradient of the site. Now, an important thing to remember about Paiute Mesa is, even though the number of tests were relatively small, I think there were a total of 82 nuclear tests that were conducted up there, the amount of radioactivity associated with those tests was quite large. Over 60% of the radioactivity that the UGTA program has to address resides on Paiute Mesa, and 45% of that is in western Paiute Mesa. So this is relatively important because the distance to off-site receptors is shortest for all of the CAUs from Paiute Mesa down to Beatty, which is just off the map right over here. Well, actually, you can see the distance right there. There's Beatty down in there. So we didn't actually, even though the UGTA program started characterization activities in 1993, we didn't actually begin activities on Paiute Mesa until about 1991, or 1999. This was our first phase of characterization. We thought it was going to be our only phase of characterization. And when we started, we drilled and tested 8 wells up there. We conducted multiple geophysical surveys. We conducted geologic mapping and modeling. We did recharge studies up there. We used geochemistry obtained from the wells that we drilled and pre-existing wells to conduct geochemical mixing models to better understand where the water was flowing from and where it was flowing to. We explored the radiochemical source term to better understand what the contaminants of concern could possibly be. We conducted a tracer test to look at how surrogate contaminants could be moving in the rock. We explored the role of colloids in terms of their ability to facilitate migration of radionuclides that would otherwise be immobile. And we conducted a number of laboratory studies, including studies of matrix diffusion, how easily some of the contaminants will move from fractures into the surrounding rock. This happens to be a picture of one of the wells that we drilled at that time, EC2A, back in January of 2000. So all of this data from the phase 1 characterization was assembled and used to develop a flow and transport model. And just one of the many results is shown here. And what I want to show you here is the drawing on the left is a picture of the particle path lines from the various underground nuclear tests. And if you look over in this area, here's Hanley, and here's PM3. Well, you can see that some of the lines actually connect the two. So the model was giving us an indication that our prior conception of this flow based on the potentiometric trough may actually be wrong. But simultaneously with that, if you look at some of the transport distances, and that's what is shown here, these are transport distances in 50 years, there was really no transport from Hanley to PM3, and the reason for that is that these rocks were thought to be geothermally altered, so we didn't think that the permeability was very high, we didn't think there was a lot of water flowing through there, so the model itself predicted contaminant transport would be minimal in that particular area. But you do see that within 50 years it was predicting extensive transport down to the south, past wells that we knew the contaminant transport wasn't actually occurring. So internally, we knew that this was a problem. And so DOE consulted with NDEP and made a decision that we're not even going to publish, we're not even going to proceed with this phase 1 model. We're going to start a second round of characterization. And this is the first exemplary item that I really want to highlight for you, is our ability to take a look at our results and see if they fit the facts, and being able to step back and iteratively go back and recharacterize, conduct additional model evaluations if we're in that particular stage of the FFACO process, or even in the closure stage, to keep on reiterating and looking at our results to see if they fit the facts. So this is a really powerful tool when dealing with uncertainty, and it's explicitly embedded in various parts of the FFACO strategy. So this is, again, the first exemplary item that I wanted to highlight for you. So based on that, starting in 2009 and continuing to today, we embarked on a second phase of characterization out at the site. We drilled an additional 10 wells. We tested and sampled them. We updated our geologic model. We conducted a very refined water level analysis at multiple wells up on Paiute Mesa, which allowed us to refine the potentiometric surface. We conducted 16 interference tests, where basically we pumped one well and looked at the responses of surrounding wells. We revisited the radiochemical source term analysis. We conducted additional fracture analysis, and we built a simplified 2D analysis, or water balance model, that balanced the amount of infiltration and upgradient flow coming onto Paiute Mesa and balanced that with the discharge that was observed in Oasis Valley. So this is a picture of one of the wells that we drilled, EREC14, back in 2012, and some of the local wildlife up on the ridge above while we were drilling. So simultaneously with this, UGTA is percolating along, moving slowly through the FFACO strategy, but there's also these pre-existing groundwater monitoring programs that are being conducted by DOE to make sure that worker safety, the environment, the surrounding populace are protected, because we haven't finished our job on the UGTA project. And one of the wells that they were monitoring was well PM3. So PM3 was drilled in 1988 to address the hydrogeology of the area just northwest of the calderas. Remember where I showed you its location in a previous slide. And when we drilled it, we sampled it for tritium, and we had fairly low tritium levels. Just to give you, this is in becquerels per liter, because that's what they want at Waste Management. But there's 1 becquerel is equal to about 27 picocuries. So just multiply anything I talk about by 27, and that's what you're used to seeing. So this is a pretty low number. We were pretty satisfied with it. And then we didn't go back and sample the well for about 10 years. We came back in 1999 to resample the well as part of this phase 1 investigation that I talked to you about earlier. And we got some really high hits. And this was extremely concerning to us because we had the prior data. We knew that nothing was there, and it was a real issue. Well, we went back and looked at process knowledge within a few days of getting the preliminary results, and we knew that we had brought a contaminated baler with us. We grabbed one. I was there that day. We grabbed one out of the wrong pile. We thought it was clean, and we sampled the well, and it was contaminated. So within a month and a half, we went back to the well, sampled it again, and got results that were very similar to those that were collected in 1988. What happened after this is we pretty much started monitoring this well on an annual basis. And so here you see all of the results that were collected in between 1999 and all the results here. Now the closed symbols were a positive detection above the minimum detection level, and the open symbols, the crosses and the minus signs, are they were below the detection level, but we reported it as if it was at the detection level. So everything was pretty low. We would get these little episodic hits slightly above the detection limit. It was our opinion that it was the water in the well was relatively stagnant, and that it was basically maybe residual contamination that one could associate with the contaminated baler being introduced to this well. Well, that continued just fine until around 2009, 2010, when we started seeing a increase in the concentrations of the detections, and we were also simultaneously detecting them in the duplicate samples that were collected along with the primary samples. So we knew that something was going on. The program that does this monitoring is the REMP program. You've heard us talk about that before. They went back the next year, showed that actually the levels were there at the same levels that they'd seen before, just a little bit higher. And then within the UGTA program, we knew that we had to go back and investigate because something was really going on with this well. So we replicated the baling exercise, got our own positive detections, and then we went back and pumped the well, and that's these samples right here. And all of that data combined showed us that something was contributing tritium to this well in a fashion that did not agree with our prior conceptions of what was going on. So one of the first things that DOE did is the communication of the sampling results. They verbally notified NDEP. They came to this group here, gave you a presentation on the results. The results were published in the annual site environmental report. And then we also held town hall style meetings in the communities that are down gradient of the NNSS and presented the results there as well. And this is another exemplary item that I wanted to highlight for you, is this open, transparent communication of the results as we find them. This is really important to us, and for a number of reasons. One is we need the trust of our stakeholders, and so this open transparency is a way of engendering that trust with you. And then also it allows for a really open dialogue with our regulatory authority and getting their input in real time. So another thing that the DOE did after we got these positive detects is they wanted to place the results in the context of what we'd seen at this well in the past. So they collected all the data that we had about PM3, the geochemistry, how the well was constructed, how it was, the recompletion was revised at a point in time. And they wanted to identify the potential sources of tritium, and we sort of pounded our heads against the sand and came up with a number of alternatives, a surprising number that we thoroughly evaluated. And then DOE convened a panel of subject matter experts that got together, looked at all the potential alternative hypotheses, and then evaluated them to determine which one was most significant. Now, one of the members of that panel was a member of NDEP, and that it was really, really useful for us because we got to get their feedback in real time. We didn't have to sit around, propose an evaluation strategy to identify the most likeliest or most important hypothesis and then develop a characterization strategy and present it to them. We were getting their input in real time, and that was another exemplary item, this close integration with your regulatory authority. And it's something that, frankly, some of the other sites could emulate. So I mentioned that there were a surprising number of alternatives, and I wanted to explain some of those to you. So if you look at PM3, which is down here, and then you see these blue lines running up through here. Well, this is the surface drainage pattern for surface water that drains, and the closest that this comes is about 300 meters away from PM3. Notice up here, these are two plowshare tests, Palaquin and Cabriolet, and the surface water drainage actually drains part of the fallout plume from these two tests. So one of the things that we were thinking was, well, maybe it's not groundwater transport from an underground nuclear test. Maybe what we're seeing is surface water transport down the drainages to close to PM3 and then localized infiltration here. Well, this particular gamma map that was made to map out this plume here was conducted in 1999. These tests were conducted in the 1960s. So from a gamma ray point of view, there doesn't seem to be any redistribution of this fallout along the channels. Now, tritium might have done it. You can't pick up tritium with these types of maps, but certainly some of the other radionuclides that are gamma emitters weren't moving in the channels at all. So that made it a little bit less likely. There's a certain aspect of the construction of PM3 that would facilitate localized infiltration. I told you that we recompleted it. Originally, it was just an open hole, and then we came back and put in these two piezometers here. And if you'll notice, there's a gap that runs from basically, I think this is about 100, 120 feet below land surface, all the way down to almost above the water table right here. Any water that can infiltrate down this far has immediate access down here. So if there was localized standing water near the well, and it could infiltrate locally, its path down to the water table is really, really short. Now the Navarro went out and looked at the wellhead. They tried to see if there was any evidence of standing water adjacent to the well, and they really couldn't find any. So that tended to negate that particular hypothesis. One of the questions is, well, how do you get tritium into something like that? These plowshare tests like Palaquin and Cabriolet and Schooner up here, which is where this data is from, breathe. During atmospheric pressure changes, you know, the atmospheric pressure lowers and gas that's in the vadosone will come out of the ground. Well, when it comes out of the ground during those periods of time, it can carry tritium vapor with it. And this is a record of the tritium coming out of Schooner. It's measured right next to the crater itself. If that tritiated plume can flow along the ground and interact with a standing body of water, whether it's just a shallow pool adjacent to the wellhead or maybe drilling fluid that was used to drill the well, and if that was injected downhole, that could be a potential source of tritium. And then finally, once we had started the phase 2 characterization, I told you that we went back and reanalyzed the potentiometric surface in that area. These blue lines here are the revisions that came out from that. And you can see now that Handley is looking like it's much more upgradient from PM3 than the prior version that I showed you. Also, if you look at the traces of the fractures, the general direction of the fractures, which are in this direction, that even makes it more likely that Handley is down gradient, or PM3 is down gradient from Handley. This thorough evaluation of alternative hypotheses as to the source of tritium in PM3 is, again, an exemplary item that I'd like to highlight for you because it allows us to really just lay out all of the data that we've got and really pore over it in order to better understand what's going on at the site. Once we had gone through and identified these potential hypotheses, we began to come up with, well, how do we characterize these things? What would you do that needed to be done? And so one of them was just, well, let's just monitor PM3 and do nothing. Let's just continue looking for tritium and see if it gets to a point where it really becomes of a concern, because all of the detections are well below the Safe Drinking Water Act. Another proposal was to include chlorofluorocarbons and noble gases in the monitoring program so that you could look for indications of recent infiltration at the site. We proposed shallow drilling in the nearby ephemeral wash to see if we had radionuclides at depth there. We looked at drilling either a single or multiple characterization wells between PM3 and some of the possible underground tests that could have contributed to tritium via advective groundwater transport. The recommendation as to how to proceed was really a pragmatic one. The panel of subject matter experts felt that Hanley really was the likeliest source, and that was consistent with the slow increase with tritium over time. When we pumped the well, we also saw very, very low traces of carbon-14 and chlorine-36. Nothing that would be a concern from a health point of view, but certainly was slightly above the natural average that we see in groundwater on the site. And the only way you can get that is through advective transport of groundwater. And frankly, the advective transport by groundwater is the only pathway that's subject to regulatory oversight, and that was one of the ones that was supported by the in-depth member on the committee. So the decision was to pursue that one. Once we got into, and again, that comprehensive evaluation of the alternative hypotheses and then developing multiple characterization strategies to address each one is, again, a very, very important process that I'd like to highlight for you during this particular characterization approach. Once we came to the decision that we were going to drill a well, the decision was to drill one well, and that well eventually became ER20-12. Now, when we began to design this well, there was a lot of uncertainty. We didn't know where the tritium would be in the subsurface when we drilled it. And we have a mandate from the state that we cannot allow contaminated water from an aquifer that has contamination in it to affect another one that is clean. So we had to basically design the well and drill it in light of all of this uncertainty. So we basically mapped out all the potential pathways that one could encounter based on all the aquifers that we saw there and whether they were contaminated or not, and what we would do if we saw what we thought might be there. And so there's these multiple pathways that one proceeded down there. This approach is actually, there's a formal name for it. It's called Terzaghis uncertainty method, or the observational approach is how they use it in environmental endeavors. And this was employed in the design of this well. And it's a method for dealing with uncertainty when you have to construct something. And it's a very powerful tool, and again, something that some of the other sites should emulate if they should have some need to do so. Once we got to the construction phase, it was a very challenging environment. The location, which you can see the contours here, this was the pre-existing road. We had to kind of find our path up to this knoll for the site of 20-12, which was between PM3 down here and Hanley up here. So the surveying and the construction was challenging because we had to deal with these fallout plumes. The topography was rough, and we had to work with that as well. And so it took quite a work to be able to build the site. The site's on the side of this knoll here, so a lot of dirt had to be moved in order to drill the location. Once we actually started the drilling, it was in October when we started drilling, and we drilled through the winter. The winds were really high. And we were getting these really energetic discharges. Once we got into the groundwater and it was contaminated, we had to figure out a way to protect the workforce. And so we built these big wind walls. We built these discharge abatement structures in order to protect the workforce. And there were multiple things that were going on in order to protect the workforce. The distance from this well site to the closest medical facility was on the order of about 47 miles. So they actually had EMTs stationed on site in case of an accident. Of course, we had radioactive plumes that we were drilling through, so we had rad techs on location. The wind abatement structures just are a very physical demonstration of the extent that DOE went to protecting the workers while they drilled this site, and is again another exemplary action that I'd like to highlight for you. these wells are just really expensive. And so we want to collect as much data as we possibly can while doing it. And one of the ideas that we had is, well, we're going to drill this well, but we're really not going to know whether or not it's hydraulically connected to anything. So we know that when we drill the well, we completely empty it of water. And so let's monitor some of the surrounding wells to see if we get a hydraulic response during drilling. And we did exactly that. So this blue line is the water level in PM3 during the drilling of 20-12. And once we penetrated one of the tough confining units, you saw this very dramatic, prompt drop in the water levels while we dewatered the other wells. So we knew, even while drilling, that PM3 was hydraulically connected to 20-12. And that's part of the story that you need to know in order to believe the groundwater transport scenario. Once we finished drilling the site, we completed it in 5 different zones where we felt water was entering the well, and so that we could sample these different hydrostratigraphic units. And we found tritium throughout the profile, with the highest concentrations up in this aquifer here, and then lower concentrations down here. Here's the Handley test, and then there's well PM3. This broad distribution of tritium in 20-12 was diagnostic of advective transport by groundwater. So our evaluation process was spot on. So the overall results of the characterization at tritium, the characterization activities at 20-12 was that the tritium profile within that well can really only be attributed to Handley, and that that tritium is likely the leading edge of the plume as it was observed in well PM3. And then here we have a picture of 20-12 while it was being drilled. And to summarize some of the challenges that we had to deal with, we had that detection of tritium in PM3 in 2010. I mentioned earlier it was 2009, but that was wrong. That gave us some pause because it's 3 kilometers from the edge of the corrective action investigation unit for Paiute Mesa, and more than 7 kilometers from Handley itself. So that implies a fairly rapid groundwater velocity, at least for the leading edge of the plume. The detections of tritium in PM3 were episodic and very low level and were not replicated in duplicate samples, so it took us a long time to figure out what was really going on. The site is characterized by this complex geology, these intercalated calderas, really thick geologic sequence of volcanics, the great depth to water, it's remote, high elevation, subject to inclement weather. We had this residual surface contamination that we had to deal with. And then we had all these competing hypotheses as to what the source of tritium really was. And again, to highlight the exemplary actions taken by DOE, the flexibility that's implicit or explicit in the FFACO strategy is a really powerful tool for dealing with uncertainty and for when we encounter things that don't quite meet our expectations. This prompt and open communication with the stakeholders is, again, a really powerful tool that other sites should employ. Incorporation of the regulatory authority into the technical advisory committees is something that we do, and not just for this site, but for several of the other ones. And again, we get that prompt interaction that is so critical to us to be able to move forward. The thorough evaluation of the alternative conceptual models and the pragmatic approach for the selection of the characterization strategies was, again, an exemplary item. The observational approach used during drilling, the safety first mantra that was employed, and the opportunistic data collection that was utilized at the site are all things that I wanted to highlight for you. And with that, I think it's the end of the slideshow. So are there any questions? Yeah.
If I understand correctly, you found that groundwater was the particular problem. So when you were drilling ER 20-12, did they do any kind of analysis as to where the groundwater and the period of time, I'm sure it's rain, might have imprinted itself in those particular areas? And did they test for moisture content as they went down?
We don't typically analyze the drill cuttings for moisture content. We know that Paiute Mesa is subject to recharge and infiltration We just assume that based on our overall models. We have general estimates like that water balance model that I referred to.
Yeah.
That gives us a kind of a confining upper estimate of what infiltration could be at these sites. This site is elevated enough that one would expect at least a small amount of infiltration to occur. But it would be really difficult to be able to get the tritium that if it was from a local source and through infiltration, how do you get it so deep in the saturated profile? There's really no way to do that from localized infiltration. Yes?
Is there any other sample wells that are farther out in the flow path, farther out than 2012?
Yes. There's, I think down gradient, there's EREC14. I don't have the map, but I know there's a couple of them out there. Basically, you've got that Thirsty Canyon lineament that's coming down through here, and we've got a couple wells, and I believe EREC14 is the next one that's down gradient. And we've not seen anything in that well. I don't trust me on the name. I think that's right. Okay.
Could you use the microphone? Thank you.
Thought I was going louder now. Has the concern increased over the possible movement of the heavier elements such as plutonium, colloidal movement or?
We have sampled that well for the full geochemical characterization suite that we normally do for all of our characterization wells. And we do analyze for plutonium. I have not seen those results. So Ken's not here. Ken Rayfield would know. But I don't know, right? Irene, do you know? Yeah, I haven't seen those results. I mean, the tritium concentrations they're kind of low for seeing some other things there. Typically you start seeing other things, in 100,000 to million picocuries per liter of tritium, and we're approaching the 100,000 mark, but certainly nowhere near the million mark. So I would be surprised. I mean, it might be on the colloidal fraction, but we haven't looked at that yet.
Okay, I just know that the ones that went off up in 1920 were in the higher yield, and I'm sure that they created new fractures and changed some of the old fractures that was always there. It could have changed some of the permeability of the mesa itself.
Yeah, Handley is greater than 1 megaton, so it's a very large test. Certainly within several cavity radii, their fractures were mapped as a result of that would have fractured the rock, but we're a long ways away from that. So to see test effects that far out, like at 20-12 or certainly PM3 would be almost unheard of.
Okay, thank you.
All right, well, thank you very much.